Okay, cool. I know it's right before lunch, so I'll try to keep it short and hope that you all bear with me. I'll give you an update on the VitroJet. So VitroJet, for those of you who don't know it, it's a tool for sample preparation for cryo-EM, and it's made by CryoSol. CryoSol is a spin-off company from Maastricht University, and it got founded to be really focused on sample preparation for cryo-EM. So actually, I saw this graph a few times yesterday, and I changed my first slide because it actually made me wonder. So you see, cryo-EM is really increasing the amount of structures that are deposited into the PDB. But we also saw this overview yesterday. So it's the overview of the microscopes, of the high-end microscopes all over the world. And it made me wonder, how effective are these microscopes actually used? So if you look at the number of structures that got deposited into the PDB last year, it's a bit over 4,000. And if you look at the number of microscopes that we have, it's over 700 high-end microscopes. So if you calculate it, then every high-end microscope only produces one structure in the PDB every 2 months. So I asked a few people, how is this actually possible? And of course, these microscopes are used for tomography, and maybe not all structures are uploaded into the PDB. But if you really compare it, that one structure for 60 days, and a data collection only takes a few days. So there's still a really big gap. So I asked them, what's actually the main limitation for uploading more or creating more new structures? And of course, there are more factors, but sample preparation is clearly one of the main limitations at the moment. So this is how we see sample preparation. Happy to chat with you about it if you have a different view. But you have a grid that comes in, and you have your sample, of course. The grid gets glow discharged to make it clean and hydrophilic. Then you make a nice thin layer, you deposit it onto the grid, you vitrify it, and you put the grid into the screening microscope. So when you're screening, you look at evaluating the grid, and you do that based on a number of criteria. So I split them up here into two different things. So a number of criteria belong to the grid preparation itself. They don't, I mean, of course, they influence the sample, but they are not really that related. So your layer thickness, vitreous ice, the grid should be intact, contamination. And then there are a number of criteria with the samples. So you don't want it to aggregate, you don't want it to fall apart, and have random orientations. So in your screening microscope, you basically check, okay, do I go another iteration? Do I do another round of sample prep? Or do I go to data collection? And if you look at this whole process and all the steps that are involved, then actually it's maybe not that strange, because it's quite a complex process. There are a lot of variables in this process, and you only see the result at the end in the microscope. So if you look, for example, also at grid preparation, then this glow discharger is usually a separate device. Then you have blotting, which is anyway kind of a magic step. You vitrify it, and afterwards you need to fiddle with this grid. You need to put it into an auto grid ring, clip it. And if you compare all these steps in grid preparation, if you compare it to the automated handling in the microscopes, automated data collection, and on-the-fly processing, then there is a really big difference between how we do grid preparation and how we deal with the samples in the microscope. So this is also what at the start of the VitroJet project was the main aim. So it's like, okay, if we now first control this grid preparation and really focus on the criteria on grid preparation to have them under control, then we also can make the next step. If we don't have a solid basis, of course you have some lucky shots, but yeah, it's nothing to really do systematic and fundamental research on. So we combined a number of new technologies. So we integrated a plasma cleaner. We do sample deposition by pin printing and jet vitrification, so we can vitrify pre-clipped autogrids. We combined them into the VitroJet, and the idea is really to, because we can vitrify autogrids with the jet, to really fully automate the system, and the user prepares everything up front, and afterwards you just fill in your settings, and the machine does the grid preparation for you. So that's shown in this animation. So you can put in any type of grid as long as it's pre-clipped into an autogrid. You can see that over here. So a grid cassette with up to 12 autogrids. Then for every grid, you have a pin for the deposition. Then you have a pipette that picks up 0.5 microliter of stock volume, goes into the machine. You cool it down, and then you fill in the settings, and the machine automatically loads pin number 1, picks up the first autogrid automatically, and then it's moved down to the integrated plasma cleaner. It's cleaned. Then the pin dips into the pipette, picks up a little bit of sample and writes it onto the grid. The autogrid goes down and it's jet vitrified to cool it down from the center first and then the ring. And it's automatically stored into a grid box. So then you have the option to repeat this cycle for up to 12 grids. Once you're done, you're done. The cryo module comes out, and you can take the grid boxes and load them into the microscope right away. So this is basically very short the process that's going on, and the jet vitrification is, of course, a very important technique to vitrify these autogrids and to automate the whole grid preparation process. But there are not that much exciting results that you can show other than vitreous ice or an automated system. The other thing that's really important is the layer thickness. And as Bridget Carragher also showed yesterday, if you have a very nice and good ice layer, then only 10 images of aldehydes are enough for a 3 angstrom reconstruction. So I'll show some of the results. This is a collaboration that we're doing with the group of Simone Mattei at EMBL in Heidelberg. And here we really want to measure the accuracy of sample deposition by pin printing. So I'll show you here a schematic overview of the pin printing. On top, there is a solid pin. The bottom is a cross-section of the grids. So you see the grid bars and the perforated foil. And the sample is located in between the pin and the grid. So we move around this solid pin, and with that, we create a very thin layer. So it's actually quite a simple process, but that also makes it much easier to control, of course. So you have to see this pin and the grid are both hydrophilic. So the sample wants to stay in between. And if you move very slowly, then your sample just follows the movement of the pin. Once you move faster, then the sample has more difficulty to keep up with the movement of the pin, and also you create a thicker layer. So what we did is we vitrified a number of grids with different writing speeds, put all of these in a microscope, and there we did measure the thickness for each individual hole. So image with and without energy filter, find the holes, and then determine the layer thickness. So these are some of the examples. So this is a map of a grid that was printed at 0.25 millimeter per second, so at slow velocity. And this is actually for each square, we made a montage of 3 by 3 tiles. So each square is 9 images, and these were reconstructed back into an atlas. Maybe it's a bit difficult to see here. but the holes, they are color overlaid, and it's a blue color, so that means that it's thinner ice. Then if you go medium velocity, then the holes get a bit more green. Even higher, then they get more red yellowish, so it gets a bit thicker. And even higher, then it gets even much thicker. So these are 200 mesh grids. The deposited area is in total 800 by 800 micron. And with this pin printing, in this example, we started from the center and then we made a spiral outward to really cover part of this 200 mesh grid. So now we have for each grid, we have found the holes and we have determined the thickness for each hole individually. So we can put that into a histogram. That's shown over here. So the blue histogram is for the slow velocity. Then you can see you have a thickness of somewhere between 20 and 35 nanometer for most of the holes. If you go faster, if you go 1 millimeter per second, it's 30 to 40. For 4 millimeter per second, it gets even thicker, so it's 40 to 60 more or less. And at the highest speed, for this example, at least for this sample, it's at 60, 70, 80 nanometer. So this kind of shows how we can control the layer thickness with pin printing. We repeated this experiment for in total now 36 grids. And next week, I'll also go back to EMBL to collect more data and to really strengthen this analysis that we're doing. So being able to control this layer thickness is, of course, very nice. But to check it and to measure it before you put it in the microscope, that's even more valuable. So this is a collaboration that we do with the group of Karsten Sachse at ERC in Jülich. Because while we are pin printing, we also have a camera that monitors the deposition. So you can see that over here. This is a movie, so the pin will approach in the center and it will make the spiral to deposit a thin layer on the grid. So we make this movie for every grid. So you always have this information. And we've done some data processing on these images because you have, of course, you have an image before deposition and you have an image after deposition. And you can use both images to do some motion correction, find individual holes, and then determine the intensity where you can correct also for the background of the empty grid. So after that, we basically put the grid again in the microscope. We do a similar analysis to what we did before. So we make images with and without the energy filter, find the holes again, and determine the layer thickness with the mean free path. So if we now look at the results, then on this one, you see the image of the deposition. And now if we look at this background corrected intensity of the VitroJet camera, for each individual hole, we can make a color overlay again on this system. So you see the thickness distribution over the grid for every individual hole. In the bottom, the grid is not exactly in focus because it was not perfectly flat in this case. Then we have the same grid in the microscope, and we also have the data where we measured for each of the same hole the ice thickness. And then you can actually see that both match very well. So it's possible to, based on individual holes, already measure the ice thickness before you put it in a microscope. And we now did this for a number of grids. I think in total we have around 100,000 holes that we compared the intensity with the thickness. And we see that it's a very good match. I think more or less 15 nanometer accuracy, we can, down to 15 nanometer accuracy, we can actually estimate this layer thickness. I cannot show it here because we're writing a publication about that, but happy to talk about it a bit more in the future. So these are some results from our customers, shown on the right. just showed some examples to show a variety of different samples that were tried at our customer site so far. So there are some filaments, virus particles, bacterial phages, membrane proteins, soluble proteins, and also with various different sizes. So some are very small, some are very big. And these are just some examples to show, but I leave it more up to them to explain more what they did in these experiments. So that brings me back to the overview again of sample preparation. And I think that we're now really hammering down these first steps of the grid preparation, really getting a good control over these 4 things. And that's basically the basic condition to really take the next step, to have a good foundation for looking into more challenging samples. So it works, of course, for a lot of samples, but we always want to push for samples that don't work so well. So in the VitroJet, as I showed, we also included this visual quality inspection to measure the layer thickness. So if we add that step, then this enables us to also use the microscopes much more efficiently and much more useful, of course. And then we can have a look at, okay, if there are proteins that don't behave well, why wouldn't they behave well? A lot of people, of course, point to the biggest suspect of the air-water interface. And I think it was also mentioned that each particle hits the air-water interface in less than a millisecond. So if you have a sticky sample, then it's quite difficult to outrun this. But there are also other approaches. So for example, in the grid making, there is a lot of developments. On the left, you see this was done in the lab of Faisun at IBP in Beijing. They're making nickel titanium grids that we are actually routinely using at the moment, which have lower affinity to particles. And of course, the LMB is working on these hexagold grids. We haven't been able to test those, but in principle, any grid can be used in a VitroJet. So that makes it a very nice and very flexible system. And besides that, there is a lot of buffer optimization, screening with detergents or additives. And if you work very hard to get a sample, to get a volume of 10 microliter, then if you use blotting, you can make 3 grids out of this. But in the VitroJet, you only use half a microliter of stock volume. And then for each grid, you use around 1 nanoliter of sample. So you could make easily more than 200 grids with the VitroJet with this. So we think that this solid base of grid preparation, in combination with the flexibility to use any grid and to use a very low volume, that this already proves to be very valuable. And it's also ready to scale everything up in the future. So with that, I would like to thank our customers, collaborators worldwide. It's really nice to work together with all of these great labs. And I would like to thank you for your attention, of course.